Hello everyone, welcome back once again to C++ Real-Time Audio Programming with Bela. This is a course about creating the building blocks of modular synths and audio effects using the C++ programming language. Today, we're going to be looking at the digital inputs and outputs on Bela, which we'll see in the context of gate and trigger signals used on modular synths. We'll also look a bit further at control voltages, which we started looking at in the previous lecture. Today, then, you will learn about Bela's digital I/O, you'll learn about working with LEDs and push buttons on the breadboard, and we'll see what we mean by gate and trigger in the context of synthesizers and how we can implement these things with digital inputs and outputs. By the end of this lecture, you will have made a noise generator and also a step sequencer controlled by a push button. As always, you can find the companion materials, including code examples for this lecture, on the GitHub link at the bottom of the screen. To follow along with the code examples, you'll need a Bela starter kit or a Bela mini starter kit. This lecture will also make use of some other components, including an LED, a push button, some resistors, jumper wires, and a breadboard. A complete list of components can be found on the companion materials. To begin, let's review the capabilities of the Bela and Bela mini systems. Bela provides stereo audio input and output, and 8 channels each of 16-bit analog input and analog output. Additionally, Bela provides 16 digital I/Os, which is what we'll be focusing on in this lecture. Bela Mini provides a similar set of capabilities, though without the 16-bit analog outputs. You can use either a Bela or a Bela Mini for this lecture. In the previous lecture, we looked at using an electronic breadboard, and I'll review this briefly now. The breadboard is essentially a way of connecting different electronic components together. Each column of 5 holes is connected internally by a metal strip, such that wires put into the same column will be connected together. The same is true of the other side of the breadboard, but there's no connection across the break in the middle. This allows us to put integrated circuits in the middle of the board. At the edges of the board, you'll typically find long strips, which are entirely connected together. On some breadboards, these are labeled with blue or red stripes to indicate their usual function, which is to connect them to power and ground to make it convenient to access these signals in your circuit. In a moment, we'll talk more about the pin numbering of the digital pins on Bela. I encourage you to follow along with this in the interactive pin diagram, which you can find in the IDE. Just mouse over any of the green squares which represent digital pins, and it will tell you the number of that pin that you can use in your code. Let's start with the full-size Bela board. Bela provides 16 digital inputs or outputs. These are located on the long black rectangular headers on the edges of the board. These connectors are called P8 and P9, which is the name given to them by the BeagleBone Black on which Bela is based. Of course, you'll notice that there are far more than 16 pins available on these external connectors, and many of them are used by the BeagleBone for other functions. You can find the complete details about what the BeagleBone does with these pins in its system reference manual, which can be found at the link here. For Bela, we're only interested in the 16 pins that are easily accessible to the Bela API. To be able to find these, it's important to understand the pin numbering of these connectors. When the board is oriented, as shown in the picture, pin 1 is located in the upper left-hand corner, and then the pins are numbered as shown. There's a total of 46 pins on each of the P8 and P9 connectors. Some of these pins will hold the digital I/Os, other pins will hold signals like power and ground, as we'll see in a moment. The situation is similar with the Bela Mini. Here the connectors are called P1 and P2, which is the nomenclature used by the Pocket Beagle on which Bela Mini is based. Once again, there are 16 digital I/Os available on these connectors, along with power and ground. On the Bela Mini, the functions of the relevant pins are labeled on the silk screen on the top of the board, but again, it's also available in the interactive pin diagram. I want to emphasize one extremely important point about working with digital I/O on Bela, which is that they should only be used with 3.3 volts and never with 5 volts. The digital pins are not 5 volts safe because they connect directly to the processor of the BeagleBone. If you put in a 5 volt signal, you will damage the board and it will no longer boot. Therefore, be sure that you only use 3.3 volt logic consistently throughout your circuits. Before we look into any of the theory of digital inputs and outputs, let's build a first example project. I'd like you to build up this circuit on your breadboard. It requires an LED, a push button, and 2 resistors. Notice that each of the resistors has a different value. The push button has a 10K resistor, which has the color bands brown, black, orange, and gold. Then for the LED, you can use a smaller resistor between 220 ohms and 560 ohms. So in this case, I recommend red, red, brown, gold. Be sure you put in both the button and the LED in the correct orientation. For the button, notice that you're using 2 adjacent leads of the push button on the same side of the device. For the LED, the long lead should go to the resistor and the short lead should go to ground. And here we can see the equivalent circuit for the Bela Mini. Once you've built up this circuit, open the example called Digital I/O, which is located in the companion materials for this lecture. Drag the zip file onto the browser and it should prompt you to create a new project. The project is complete, so when you run it, you should find that when you push the button, the LED turns on and you hear a noise through the headphones. Alright then, we have the Digital I/O project loaded on the board, and we can run it. And we'll see that when we press the button, we hear the noise. Okay? Now let's talk a little bit about the theory of the digital pins. Digital input and output is oftentimes known as GPIO. That stands for General Purpose Input and Output, to contrast it with specialized digital buses. Digital I/Os are contrasted from analog I/Os because they only have two valid levels, either high or low, which is sometimes represented as 1 or 0. The voltage of this depends on the particular standard that you're working with. In the case of Bela, the digital I/Os run at 3.3 volts, so a logic high will be a value of 3.3 volts, a logic low will be 0 volts, and nothing in between is a valid level. What is unique to Bela is that the digital inputs and outputs are treated as sampled signals, just like audio or analog. They're sampled at 44,100 samples per second, also like audio. However, unlike audio, the possible values are only binary, 0 or 1. Bela provides some functions to work with digital input and output. As we saw in the last lecture, these functions take not only which pin you want to read, but which frame you want to read it at. The reason for that is that these are sampled signals and we are processing by blocks, such that every call to our render function is going to have multiple frames within it, and we have to specify which one of them we want to read. The digital read function, as its name implies, will read a given digital pin, returning its value as an int. The digital write function, by contrast, will write a value to a given pin. The arguments we have to pass are the Bela context, which is the data structure which holds the actual buffers for this data. We have to pass it the frame, which indicates when we want to write it. We pass it which pin we want to write to, and then we pass it the value in the case of digital write. Now you might reasonably ask, with 16 digital pins, how do we know which pins are the inputs and which pins are the outputs? The answer is that any digital pin could be either an input or an output, and it's up to our code to tell the pin which one to be. To do this, we have another function called pin mode, which can tell a pin to be either an input or an output. Just like digital read and digital write, pin mode will take a reference to the Bela context, and it'll take a reference to which frame we want the pin to change at. Therefore, we can change pins from inputs to outputs and back again on the fly. In the previous lecture, we saw that the analog write function had a companion called analog write once, which would change the value of the output for only one frame and not any of the successive frames. There are similar functions available for digital write and pin mode called digital write once and pin mode once, respectively. Now let's look at how some of those functions were used in the digital I/O example. Inside of setup, the pin mode function is called for each of the two digital pins that we want to use. This sets the LED pin to be a digital output and the button pin to be a digital input. Note that the pins default to being inputs unless you tell them otherwise, but it's good form to call pin mode for every pin that you want to use. Within render, inside the for loop, we have some code to call digital read to check the value of the button. Digital read will return high, or 1, if the button is not pressed, and it will return low, or 0, if the button is pressed. This way around, where pressing the button causes a low value, is a function of how our circuit is wired up, and we'll talk more about that in a moment. After we've checked the state of the button, we can write the digital output to be either high or low to turn the LED on or off, respectively. Notice here that we're using the digital write once function instead of digital write, because we intend to call it every single frame, therefore it's slightly more efficient to use digital write once. However, it would work to use just digital write in this context. Finally, notice that we're making use of several predefined constants in the digital I/O code. Input and output are constants that are predefined for you to pass to the pin mode function to indicate the direction. Likewise, the keyword high is defined to be equal to 1, and the keyword low is defined to be equal to 0, and you can use these in the digital read and digital write, though using the numbers is also equivalent. One other aspect of the code worth discussing is the generation of the noise itself. This code generates white noise, which is defined to be a random signal with equal energy at all frequencies. It turns out to be quite easy to generate white noise. All we have to do is generate a different random number for each successive sample. In this case, we use the following formula, and let's go through that now. First, we start with a function called rand. This is part of the standard C library, and it generates a random integer between 0 and a very large number. The maximum value will vary depending on the platform, but will always be defined for you in this constant called rand max. So what we subsequently do is divide that random number by the maximum possible value. Notice that we've typecast each of these to be a float so that we get a fractional value once the division is done. This will give us a random number between 0 and 1. We then have to normalize this to be an audio signal which ranges from -1 to 1. So the first thing we do is we multiply it by 2, giving us a range between 0 and 2, and then we subtract 1. Therefore we end up with a random number between -1 and 1 for each subsequent audio sample. In the example project, we also then scale it down just to achieve a reasonable volume level. You may have noticed earlier on that we needed 3 wires and a resistor to use the button. That might seem a bit strange given how simple a button apparently might be, but it's worth explaining why this is necessary. Breadboard buttons are sometimes known as tactile switches, and they're typically made as normally open switches, which means that when the button is not pressed, the 2 terminals are not connected, and when you press the button, the 2 terminals are connected. Here's a diagram of what these buttons often look like from the top. Notice that there are 4 different leads on this button. Why do you think that might be? One possible answer would be that there are 2 different switches inside this button, but in fact the actual answer is much simpler. The reason that there are 4 leads is just to make it easy to mount on a printed circuit board and make sure that it doesn't fall off. In fact, there's only 1 switch inside of this device, and so it's important to know which pins to use. In this case, the 2 pins that we want to connect to are the 2 adjacent pins on the same side of the package. The leads across from one another are already connected internally inside the switch. Therefore, make sure that when you put the button into the breadboard, you have it in the right orientation. It's very easy to mix up. To use the button in a circuit, we also need a resistor. The reason for this is that we need to generate a digital voltage, either 3.3 volts or 0 volts, depending on whether the button is pressed. Notice that in this circuit we have the resistor going from the input up to 3.3 volts and the button connects down to ground. If you consider the button being pressed, what this will result in is the digital input being connected to ground. That means that we'll read 0 volts and therefore a low value when we call digital read. However, if the button is not pressed, it's also important to define what the value of the pin is. If we didn't have the resistor here, we would find that the input pin was just floating when the button was not pressed. That means that the pin isn't connected to anything and could take any random value which might differ at different times. That's clearly not what we want. On the other hand, we can't afford to put a wire from the input up to 3.3 volts because then when we press the button, 3.3 volts and ground will be shorted out. That's obviously bad. So the solution is to put a resistor between the input and 3.3 volts, which gently pulls it up when the button isn't pressed. When the button is pressed, the input is pulled down, and in this way we can read either high or low. What we've done so far is to check whether the button was being held down at any given time. We knew the button was being pressed because digital read would return low. That's again because the switch is going between the digital input and ground. Other circuits might work different ways, so always be sure to check. A trickier question is how to know if the button was just now pressed. In other words, we want to detect an event when a button press first begins. How do we do this? Well, let's consider the successive frames of digital input inside our render function. Let's suppose that the button was pressed somewhere in the middle of the render function and that we had 8 readings of the digital input. The first 5 are high and the last 3 are low. The button press event takes place right here, where the digital input transitions from being high to being low. In other words, we're doing what's called edge detection. We're not looking for a constant value, either high or low, but rather we're looking for a transition from high to low, which indicates that the button was just now pressed. To illustrate this point in more detail, I want to go back to the Bela oscilloscope, which we saw a few lectures ago. Recall that the oscilloscope gives us the ability to plot a signal level over time on an XY plot. This can be useful for inputs, outputs, or any other signals within a project. In Lecture 3, we looked briefly at the triggering capability of the oscilloscope. This was essentially the ability of the scope to start drawing the screen at a particular predefined point. In particular, the screen would begin drawing when the signal crossed some threshold that we specified. There were several different controls that we could adjust about the trigger, including the mode of whether it displayed the signal whether there is a trigger or not, which channel it was triggering on, whether it was detecting a positive or a negative transition, and then also the level that the signal should cross for the screen to start drawing. Originally, we were using the trigger because we wanted to maintain a stable plot of our signal over time. but what it's effectively doing is edge detection, and it's very useful to illustrate this concept. Here I have my project running. I'll open the Bela oscilloscope, and now I'm going to go into the controls. We have two channels in this example. The first one is the digital input, and the second one is the noise that's being generated. Notice that you can barely see the red line because it's at the very top of the window. I can just change the scale here a little bit so it's a bit easier to see. The blue line is just centered on the horizontal axis at the moment because there's no signal. We'll see here that when I press the button, the red line goes down to ground, and the noise is shown on the oscilloscope. Now we can use these controls to visualize the edge when the button is first pressed. What we need to do first of all is change the trigger mode from auto to normal. What this means is that the screen will only be drawn when it detects a trigger. We will want to trigger on channel 1 because that's our digital input. We're going to change the direction from positive to negative. What that means is that we're going to trigger on a falling edge. In other words, from the button not being pressed to the button being pressed. Finally, I have to set the trigger level to something that will be crossed when the input goes from high to low. So that needs to be something between 0 and 1. We'll choose something like 0.09. Now I can close the controls at this point, and we'll see that when I press the button, the screen displays the falling edge of the red signal. And notice that the screen did not update when I released the button because we're only detecting falling edges. So if I press it a few more times, we can visualize the falling edge in each case, and the display will stay constant for us to inspect on our own time. What we're going to do in our subsequent project is write code that detects this falling edge that we see here on the screen. So let's re-ask the question, how do we know if the button was just now pressed? We know that because the current reading of the digital input was low, but the previous reading was high. Well, this raises another question. What do we mean by the previous value of the digital input, and how do we find the previous value? What we mean is that we want to know the value of the digital input on the frame right before the current one. Well, how do we do that? We need to find a way to remember the previous value, and the way that we're going to do that is we're going to store it inside of a global variable so that we have it available to us the next time around. This is slightly more subtle than it might appear, so let me just take a simple analogy. Suppose that you worked in a bakery and you used the day-old bread to make breadcrumbs for different recipes. How do you produce day-old bread? You can't at any given time just demand that the bread be a day old. What you have to do is you have to bake the bread on one day, and then you have to set it aside so that the next day when you return to the shop, it's now a day old and you can use it as such. That's very much like what we're going to do with our previous value of the digital input. At some point it will be the current digital input. What we need to do is store it somewhere so that when we come back around later, it now represents the previous input and we can use it as such. Before we get into the specific project where we do this, a bit of terminology. In modular synthesis, in addition to control voltages, synth modules are often controlled by gates and triggers. Both of these are effectively digital signals with only two states, either on or off, but it's worth talking about the difference between them. A gate is a signal that represents two states, either open or closed. For example, you might use a gate on an oscillator so that when the gate is open, you hear the signal, and when it's closed, you don't. A gate is effectively what we built in the digital I/O example, where the current value of the button determined whether we heard the noise or not. By contrast, a trigger is a signal representing an instantaneous event. This is more like the transition or edge that we've been looking at. A trigger might be used, for instance, to begin an envelope, to advance a sequence, or any number of other applications. The key point here is that we're interested in the transition. Since we've already built an example that works like a gate, let's have the next example use the button as a trigger. What we're going to build in this example is a simple step sequencer. The step sequencer is in many ways the most fundamental component of loop-based music. It plays a pattern of events in a repeating loop. Advancing the step could be controlled by a number of different sources, for example a metronome clock, but fundamentally there is always a trigger which tells the step sequencer to go from one event to the next. What we're going to do in our simple example is have our step sequencer just control the pitch of an oscillator. In practice you might also find it controlling envelopes, playing samples, or controlling other parameters. But in this case, we could implement our step sequencer as follows. We have 8 frequencies in order, and what we have is a read pointer which tells us which of the 8 frequencies we're playing at any given time. In other words, which step are we on? And every time we receive a trigger, the read pointer will advance from one step to the next. When it gets to the end, it will eventually return back to the beginning, and so play in a loop. Implementation-wise, what we're doing is we're storing 8 values inside of a buffer, or an array, and the read pointer is going to keep track of which element of the array we're reading at any given time. Then we'll use that to control an oscillator. If you've been following along with the lectures since the beginning, this idea of an array plus a read pointer should sound familiar. What does this sound similar to? Well, it's very similar to playing a wavetable, so let's compare these two. In the case of a wavetable, we had an array or buffer that held audio samples. And we had a read pointer which advanced once per audio frame. The amount by which it advanced was dependent on the frequency that we wanted to play. The idea was that we would play the read pointer, and then eventually it would reach the end of the buffer. When it did that, it would snap back to the beginning, and the whole thing would play all over again. Implementation-wise, a step sequencer is quite similar. In this case, our buffer is going to hold frequencies, or perhaps values of a control voltage. In this case, the difference is that the read pointer will only move when we receive a trigger. So this brings us to our task. In the companion materials, you'll find a code example called Step Sequencer. This example is not complete yet. What you have to do is implement the code inside of Render. And there are a couple challenges here. The first one is dealing with the current and the previous value of the button. You need to use a global variable to cache the previous value of the button so that you can detect a falling edge, where the previous value was high and the current value is low. Once you've got that working, what you need to do is advance the read pointer every time the button is pressed. Finally, you should turn the LED on and off in sequence for successive steps. Make it so that even steps have the LED on and odd steps have the LED off. Pause the video here and try it. Before we look at the complete code, I want to pull out the bit about doing edge detection on the button. Here's the global variable and the relevant bit of the render function. We're going to use the global variable to hold the previous status of the button. If you recall from one of the earliest lectures in this series, anytime we need to remember something that happened in the past, we need to use a global variable because it might have happened in a previous call to render. So here we're going to have this variable called glastButtonStatus, which we're going to use for this purpose. At the very end of the relevant block of code, we are setting glastButtonStatus to be the current status of the button. The reason that we do this is so that the next time around the for loop, it will represent the previous state of the button. Therefore, the way that we handle the previous state of the button is actually implicit in the structure of the for loop. The other thing to note about this code is the way that we handle the step sequencer. Notice that inside the central if statement, we're incrementing gsequencer location. This is our read pointer, and we check whether it reaches the end of the buffer. Gsequencer buffer is a C++ vector, so we can call this method called size to tell us how long it is. If we've reached the end, then we have to set the location back to 0. Let's see this in practice now. Here's my step sequencer code, and we can see that here is the global variable that holds the previous state of the button. In the setup function, we do some basic initialization. We set up the oscilloscope with 2 channels, and we'll look at why we do that in a little bit. We call the pin mode functions to initialize the button pin to be an input and the LED pin to be an output. And of course, we set up our wavetable oscillator, which you can find out more about in a previous lecture. Here we are in our render function then. All the relevant code is inside this for loop that counts through the number of audio frames. We're making an assumption that the number of audio frames and the number of digital frames are identical. And so if we go back up here to setup, notice that we're actually checking whether that's the case, so that the program would quit if that assumption was violated. Back down into render then, what we do is pull out the current frequency as a MIDI note number from the sequence. Once we have the MIDI note number, we have to convert that into a frequency in hertz using a formula that we've seen in an earlier lecture. Then we use that to set the frequency of 2 detuned oscillators. Here is the method that calls setFrequency for each of the oscillator objects, and then we call the process method of each oscillator to get its output, which we sum together. Here's our button code that we saw in the slide just a moment ago. We call digital read to read the current value of the button. We check if the current status is low and the previous status is high. This is our falling edge detection. If that's the case, then we increment the sequence and we wrap it around as need be. And then finally, we cache our current button status in the global variable so that the next time around it represents 1 sample old. We can also see in this example how we work with the LED. We're setting it so that the even-numbered samples in the sequence have the LED on and the odd-numbered samples have it off. This percent operator means modulo, or remainder after division. Modulo 2 will have a value of 0 whenever the integer is even. We can run this code now and see it in action. And I'll open up the Bela oscilloscope. Here we can see our wavetables. And when I press this button, we'll watch it step through the sequence. stop it there. You might have heard a couple skips in there, where pressing the button seemed to jump a step. The reason for that actually has nothing to do with our code and everything to do with the mechanics of the button. The metal contacts on the button are spring-loaded, and like any spring, it literally bounces. We'll talk about debouncing buttons in a later lecture. Let's add one final piece to this project. In addition to toggling the LED on and off and playing a tone, let's have our step sequencer generate a CV output, which we might theoretically connect to a modular synth. We're going to use the analog output for this. We saw analog input and output in the previous lecture. And remember that this only works on the original Bela board because Bela Mini doesn't have analog outputs. We stored this sequence as MIDI note numbers, and we saw in a previous lecture how we could convert the MIDI note number to a frequency using this formula. What we need to do for the CV output is instead to convert the MIDI note into an analog output voltage with a 1 volt per octave standard. Therefore, we need to convert the MIDI note number into a number of octaves. We're going to make this with respect to some reference note, which in this case is going to be the lowest one, or 36. Therefore, the question is, how do we convert the note number to the semitones above the reference? This is rather simple. We just take the note number n and we subtract 36 from it. Once we've done that, how do we convert this into the number of octaves above the reference? Well, remember that there are 12 semitones in an octave, so we can take n minus 36 and divide it by 12, and this gives us our value in octaves. This brings us to our final task for this lecture. Add CV out to the step sequencer example with a 1 volt per octave standard. Remember that the 0 to 1 range of analog out actually represents 0 to 5 volts, so you're going to need to figure out how you scale the value so that you get 1 volt per octave. Remember that the example had 2 channels enabled on the Bela oscilloscope. Use the second scope channel to log your CV out. Even if you have a Bela Mini and you can't call analog right, you can still look at it on the scope. So pause the video here, add the CV at 1 volt per octave, and we'll look at it together. Here then is my final bit of code. We've added to the end of the for loop in the render function the code to convert the MIDI note into a CV. The first thing that we do is we calculate the number of octaves above our reference note of 36, according to the formula we saw a moment ago. Then once we've calculated the number of octaves, we have to divide by 5, because we want 1 volt per octave, and a value of 1.0 corresponds to 5 volts. Here I'm putting a safety check in my code. I'm making sure that we actually have analog output channels on this device before I call the analog write once function. And the reason that I'm calling analog write once and not analog write is that I'm calling this every single frame of the for loop, so it's marginally more efficient. If you just use analog write, that also works fine, it just takes a few extra CPU cycles. Notice the arguments to analog write. We pass the Bela context. We are passing n over 2, where n is the number of audio frames. Recall from the previous lecture that in the default configuration, there are half as many analog frames as audio frames, because it runs at half the sample rate. Therefore, n over 2 will give us the analog frame that we want. We indicate which output pin we want. This is declared at the top of the file, and then finally we write to it our value between 0 and 1. We log both the output audio and the CV to the oscilloscope. So we can run this now. And we can open the oscilloscope. As before, we can press the button to advance our step sequencer. And you can see also here that the value of the CV follows the pitch contour as we would expect. Notice that we just skipped a step there because the switch bounced. This is a very common problem that we'll address in a later lecture. That's all for now. That's a basic introduction to the digital input and output on Bela. We'll continue to use both analog and digital I/Os in future projects. In the meantime, be sure to click subscribe if you want to be notified of the future lectures as they become available. Follow us on social media at Bela Platform, or check out our various online resources including the forum, the blog, and the knowledge base. See you the next time.